Good day, everyone. My name is Ifunanya Osondu, and today I will be presenting my research titled Historical Flood Validation Using Machine Learning and GIS in Oxfordshire, United Kingdom. This research focuses on validating flood susceptibility prediction using historical flood evidence collected between 2000 and 2018. We also compare machine learning models and use explainable AI techniques to understand these major factors that tend to, influence flood occurrence in the United Kingdom, Oxfordshire as a case study. So my next slide is talking about why historical validation matters. Having flood susceptibility map alone is not sufficient. Although flood susceptibility map tends to, increase support planning, disaster management, risk communication, but that high accuracy model alone is not sufficient. It must be it is equally important to verify whether these predicted flood prone areas correspond to the location that have actually experienced flooding. So this study doesn't just look at just flood susceptibility map, but also validates machine learning prediction against historical flood evidence covering a period from 2000 to 2018. And we have used about 24 geospatial predictions or predictors, sorry, compared four machine learning models and ultimately identify random forest as the best performing approach. Even though in my previous slide I had already talked about random forest as our best approach to this flawed analysis, let's look at the study objective and the workflow. Now, the objectives of the studies were in threefold. First, we had to compare different machine learning classifiers using cross validation and independent test metrics. Secondly, we evaluated how well the resulting flood probability maps agree with the historical flood observation. And thirdly, we now identify and interpret the dominant environmental factors driving flood susceptibility using random forest features. And then SHAP, sharp explainability techniques. The workflow involves preparing historical flood reference data, extracting predictors, variables, training machine learning models, validating model performance, and also eventually interpreting these results in a very clear, communicable manner. So this slide is talking about the data and the modeling design. This just summarizes the data and the modeling framework, but importantly, it looks at the variables that were imputed to train our data sets in machine learning algorithm. And we use variables that represent terrain characteristics, land surface condition, rainfall patterns, hydrology, urban infrastructure, and geological conditions. So example of this data set includes elevation, slope, NDVI, rainfall metrics, flood zones, distance to watercourse, road, buildings, and geological formation. And also for the model validation, we had to apply a 70-30 stratified train test split and also the five-fold cross validation. And the performance were actually evaluated using multiple evaluation from accuracy to precision to recall to F1 score and also full raster validation and metrics. So let's delve into the model performance. We could see that four machine learning models were evaluated. We have the logistic regression, we have random forest, we have extra trees, we have gradient boosting. But among these models, random forest dominated the strongest overall performance. It actually achieved a test AUC of 0.965, an accuracy of 0.910, and an F1 score of 0.911, also a recall of 0.918. Uh, Even if a random forest had already demonstrated the strongest performance, we still had the extra tree producing a competitive result. Random forest offered the best balance between discrimination, ability, and class level accuracy, but it made it the preferred model for this further analysis in this study area. We didn't just stop at the strength of the random forest for our model reliability. We had to assess this model reliability by examining diagnostic and confusion matrix results. And we could see that random forest achieved a correlation coefficient of 0.846, And the lowest centered root mean squared, indicating strong agreement with observed flood evidence. This model correctly identified that 2,717 flood location and 2,655 non-flood locations. Um, Importantly, flood recall was slightly higher than no flood recall, and which is desirable in flood risk assessment because it reduces the chances of missing potentially hazardous area within a study location. This slide, we are looking at the visual representation of the flood and validation probability map. We could notice that areas with high flood probability are concentrated along river corridors. You could see along drainage connected pathways and also low-lying terrain. These spatial patterns are consistent with expected hydrological processes, and you could find out that the model achieved a full raster AUC of 0.970 and a recall of 0.928, meaning that it's demonstrating excellent agreement between model prediction and historical flood record. In order to achieve a more excellent interpretation, the probability map was then reclassified into five categories, ranging from very low to very high validation. And you could notice that most of Oxfordshire falls within the very low categories, while high and very high classes cluster around hydrological connected regions. So the most important thing about this classification is that it provides a more intuitive framework for communicating flood risks and also in aiding decision making. Okay, let us look at the breakdown of this spatial distribution validation classes. We could see that the very low validation class covers approximately 1,694 square kilometer, while the very high validation class occupies about 210 square kilometer. But the important message here is that we look at areas exhibiting the strong agreement between model prediction and historical flood evidence are quite small, but they have a very high, significant portion of the county. And this is very important in our decision making when it comes to flood risk management within an area of interest. From our previous slide, we could see that we involved about four machine learning model, and a very important part of this research is the ability to explain our model, and we involved the random forest importance measures, the sharp analysis, and we were able to identify the most influential predictors. And from what we see, the most dominant drivers were elevation, flood zone, rainfall, distance to watercourse, and even extreme rainfall. And we find out that these findings are physically meaningful and aligns with established flood generator processes, providing confidence in our model predictions. In this slide, we'll be looking at uh, the interpretation of our model, and it's been broken into two columns: the main findings and also the limitations that we faced. The result demonstrates that tree-based method outperform the linear baseline model because they are better able to capture complex and nonlinear relationships. The predicted high probability flood zones are hydrologically coherent and correspond to known flood-prone environments. There's a little bit of glitch where we had historical flood inventories limitation. Not every susceptible area experienced flooding during a given period, and some flood events may not even have been recorded. So future works could explore alternative threshold or event-based validation approach to cover the gap that we face or we encounter during this research findings. As we are slowly approaching the end of this presentation, we could see that this study was informed by recent advances in flow susceptibility mapping, uh, uh, advances also in machine learning, remote sensing, GIS, and even artificial intelligence. The reference work provides the scientific foundation for applying machine learning techniques flood validation approach, AI methods such as sharp in flood risk assessment. Together, this study supports the methodology adopted in this research and highlights the growing importance of integrating geospatial intelligence with machine learning for improved flood prediction and management. We could see that I've provided a full list of references on this slide for any further consultation that you may have. In order to wrap this up, we can say that random forest was identified as the most effective model for historical flood validation in Oxfordshire. The model achieved a test AUC of 0.965, a full raster of 0.970, which demonstrate excellent predictive performance. And we also see that high and very high validation zones were mostly concentrated along river corridors, low-level drainage terrain. And also that explainable AI analysis confirmed that major primary drivers of this flood susceptibility include the flood zone, the elevation, the rainfall variables, distance to water course. They were the major drivers to flood susceptibility. Thank you once more for your attention, and I welcome any question you may have towards this research. Thank you.